Welcome to This Explainer. I am absolutely thrilled to have you here today because we're going to unpack something that literally every single one of us does, yet very few of us truly understand. I want you to picture a scenario. It's 4 a.m., you have a massive math test in exactly 8 hours, and right after that, you have a piano recital. You've been studying formulas and playing scales for days, but you still don't feel ready for either. Honestly, it's a highly relatable, incredibly stressful situation. So what exactly can you do? Okay, let's dive into this. You're faced with the ultimate dilemma. Do you pour yourself another massive cup of coffee, prop your eyes open, and spend the next few hours just cramming the books and practicing the keys? Or, believe it or not, are you actually better off closing the textbooks, putting away the sheet music, and just going to bed? To really answer that, we have to look at what's actually happening inside your brain when you try to learn something new. At first glance, our human ability to remember things can seem, well, pretty frustrating. Back in the 19th century, a psychologist named Hermann Ebbinghaus demonstrated a rather terrifying fact about the human brain. It's known as the forgetting curve. He found that we normally forget 40% of new material within just the first 20 minutes of learning it. Just think about that. You spend 20 minutes studying a super complex math concept, and almost half of it is just gone right after. But thankfully, our brains have a built-in mechanism to stop this curve right in its tracks. Let's look at how that works. Section 1. How memory works. Memory consolidation is the process by which information is moved from our fleeting short-term memory over to our much more durable long-term memory. You can kind of think of it like hitting the save button on a document so it doesn't get completely deleted when you close your laptop. And this whole saving process occurs with the help of a major, highly specialized part of your brain called the hippocampus. The actual role of the hippocampus was proven in a really fascinating, if a bit tragic, medical case. Back in the 1950s, researcher Brendan Milner worked with a patient known as patient HM. Now, HM actually had his hippocampus surgically removed. As a result, his ability to form new short-term memories was completely damaged. If you met him and left the room, he wouldn't remember you just a few minutes later. But here is the astonishing part. HM was still able to learn physical tasks through repetition. His body could learn things that his conscious mind couldn't even remember studying. And this brilliantly illustrates the difference between the two main types of memory we're dealing with. Because patient HM had his hippocampus removed, he lost his ability to form long-term declarative memory. That's the facts, the concepts, the math formulas you need for your test. But he retained procedural memory. That's the physical tasks, like the complex finger movements you need for a piano recital. So the hippocampus specifically handles those declarative facts. Building on that 1950s discovery, Eric Kandel's research in the 90s gave us our current model of how this all works. And it all comes down to neuroplasticity. When you study, sensory data is temporarily recorded in your neurons as short-term memory. It then travels to the hippocampus, which actually strengthens the neurons in the cortical area of the brain. Thanks to neuroplasticity, literal new synaptic buds are formed. It creates and strengthens new physical connections between your neurons. Your brain is structurally changing to lock in that long-term memory. Section 2. The 4 sleep stages. Let's move on and see how this builds, because we have to ask, how do we supercharge that neuroplasticity? Well, sleep isn't just lost time or some empty period of doing nothing when our important work is finished. It is an intensely active period regulated by your circadian rhythm and melatonin. On a good night, we cycle through 4 distinct stages about 4 to 5 times. Stages 1 and 2 are light sleep, your heart rate slows down, and your body temperature falls. Stage 3 is delta sleep. This is deep sleep, where your cells produce growth hormone to repair your bones and muscles. Finally, stage 4 is the dream stage, or REM sleep. Here, your body literally creates chemicals to temporarily paralyze you so you don't act out your dreams, while your brain becomes extremely active with your eyes darting back and forth just as if you were awake. Section 3. Sleep and memory consolidation. Now, what's really interesting about this slide is how we put our two pieces of the puzzle together: the biology of memory consolidation and the active, cyclical stages of sleep. When we combine them, we unlock the real secret. Notice how perfectly the sleep stages map to the types of memory we talked about earlier. During non-REM slow-wave sleep, that deep delta sleep, your declarative memory is being encoded. There's this continuous electrical dialogue happening between the cortex and the hippocampus, repeatedly reactivating those math formulas and redistributing them into long-term storage. On the flip side, REM sleep, with all its waking-like brain activity, is associated with the consolidation of procedural memory, those piano finger movements. This science actually gives us highly practical guidelines for exactly when we should go to bed, all depending on what we're trying to learn. Based on studies, if you're studying declarative facts, like memorizing your formulas for that big math test, the ideal time to go to sleep is exactly 3 hours after you finish studying. But if you're working on procedural memory, like practicing your scales for the piano recital, you ideally want to hit the pillow just 1 hour after you finish practicing.
Section 4. The Ultimate Brain Upgrade.
This totally reframes how we should look at our bedtime. Skimping on sleep doesn't just mean you're going to be tired the next day. It actively makes it less likely that you'll retain any of the knowledge or the practice you worked so hard on the night before. But beyond just passing a test, understanding this is absolutely crucial for your long-term future. So the crucial point is this. Humans roughly spend a third of their lives asleep, but today we're sleeping far less than we were a century ago. Modern lifestyles, high stress, and the constant glow of technology disrupt our melatonin production. And sleeping less than 7 hours a day isn't just bad for your test scores. It's associated with an increased risk of developing chronic conditions that could actually reduce your life expectancy.
It turns out that old piece of advice to just sleep on it is scientifically flawless. When you think about a full fifth of your body's circulatory blood rushing to your brain while you drift off, and all the internal restructuring, the new synaptic buds, and that electrical dialogue between your hippocampus and cortex, you realize that sleep is doing the heavy lifting for you. Proper sleep literally restructures your brain while you slumber. Every single time you get a full, proper night's sleep cycling through all those crucial stages, you are quite literally waking up the next morning with a new and improved brain, one that's structurally upgraded and completely ready to face the challenges ahead. So before you grab that next cup of coffee at 4 a.m., ask yourself, are you ready to wake up with an upgraded brain tomorrow? Get some shut-eye, let your hippocampus do its job, and I'll see you in the next explainer.